So let's do second part of stoichiometry. So again, with stoichiometry, you always have a new balanced chemical equation. This is a combustion of butane. So this is butane. So C4H10, two of these. So 2 moles of butane react with 13 moles of oxygen to form 8 moles of carbon dioxide gas and then 10 moles of water. So again, whenever they want to figure out how much greenhouse gas is produced by maybe butane or your lawnmowers or cars, etc., they'll use this combustion reaction. And they'll look at the mole-to-mole ratios between, like, in this case it's butane, but it can be like gasoline and carbon dioxide gas, etc. So let's look at the mole-to-mole ratios. So in this case it's a 2 to 13 to 8 to 10 ratio. So again, the only thing I did now was take these coefficients and we're set them equal to each other. So if you have a new equation, you have a new balance equation, new mole-to-mole ratios. So in this case right here, it says how many moles of carbon dioxide gas will be produced from 3.5 moles of butane. Now to look at that, I'll look at this ratio. I know that 2 moles of butane, and this is butane, will produce 8 moles of carbon dioxide gas. And I can write that as a unit factor. 2 moles of butane over 8 moles of carbon dioxide gas, 8 moles of carbon dioxide gas over 2 moles of butane. So again, same basic format. We write 3.5 moles of butane. I need to end up with moles of carbon dioxide gas. Well, I'm just going to use unit factor B. I'm going to use this. Cancels out. I'm going to end up with 14 moles of carbon dioxide gas. Now, let's go ahead and let's convert it to grams. So to convert the moles to grams of carbon dioxide gas, I use a molar mass. And again, remember, molar mass is always per 1 mole. So 1 mole of CO2 so again, always remember, molar mass is per 1 mole, so don't let that 14 sway you. So 14 moles times 44.01 grams, I'm going to end up with 616 grams of carbon dioxide gas. So let's look at the second part. It says how many grams of oxygen will react with 35 grams of butane. You know, in your vehicle or lawnmowers, you have something for your lawnmowers, you have a carburetor. That determines how much oxygen, gas, how much air you're going to need to react with the butane. In your cars, you don't use carburetors anymore, you use oxygen sensors. But they work the same way. In fact, they call it stoichiometric ratio. They use this balanced chemical equation to figure out how much air you need to react with the gasoline, or which is oxygen air, or how much oxygen you need to react with your gasoline, your lawnmowers using a carburetor, etc. So in this case right here, it says how many grams of O2 will react with 35 grams of butane. Couple of things. Remember, these ratios are in terms of moles. So in this case right here, 2 moles of butane will react with 13 moles of oxygen. So I need that ratio. I need that 13 to 2 ratio. So I write that as a unit factor. We've done that a few times. Now we write down what's given. In this case, the what's given now is 35 grams of butane. So a couple of things. If they give you something in terms of grams, convert it to moles, because this reacts in terms of mole-to-mole ratio. So this is always automatically. Convert that to moles. So I'll go ahead and do that. I'll use the molar mass. So again, grams per 1 mole. I need to get to moles of oxygen. Well, I'm going to use that second unit factor. I know that 13 moles of oxygen will be produced by 2 moles of butane. Will react with 2 moles of butane. And then I need to go from moles of oxygen to grams Again, I'm going to use that molar mass. Again, remember, molar mass per 1 gram. And so when I do that, I'm going to end up with 125 grams of oxygen. So basically, just like we've always been doing, you need mole to mole ratios, but to get to moles now, if I give you grams, you got to convert, you got to use a molar mass. So per 1 mole, mole to mole ratio, 13 to 2, and 1 mole is 32 grams of oxygen. So for the last one, in this case, how many grams of water will be produced from 7.5 of O2 of oxygen? So again, that's the what's given. It's not unit factors. So pay a little bit of attention to this. Sometimes I'll give it to you in moles to begin with, and sometimes grams. So if I give it to you in moles, we leave it alone. We don't have to convert it to moles. It's already there. I need to get to grams of water, but before I can do that, I need to get to moles. So again, remember, you go from mole to mole, and then you can get to grams. So again, I'm going to use this. I'm going to use A. I know that 10 moles of water will be produced from 13 moles of oxygen. I need to get to grams of oxygen, so I got to use the molar mass. So again, the molar mass in this case is 18.02 grams. So don't let these big mole to mole ratios intimidate you. I did that on purpose. So we just look at mole to mole ratios of each other. So if you do that, you work that out, you get 104 grams of water. So again, when you're looking at it, look at the mole to mole ratios. Again, be different for different balanced chemical equations. Set them up as unit factors. I like to have that, so I have that in front of me. Write down what's given. Again, it's never going to be the unit factors. If it's in moles to begin with, then you can go directly to the mole to mole ratio. If it's in grams, convert it to moles and go from there. And then at the end, sometimes they leave it in moles. If they don't, if they want you in terms of grams, you have to go back, look at the molar mass, and always 1 mole per that molar mass of that substance.